Hi, I'm Tommaso, PhD at Graz University of Technology.
And I'm Daniel, also a PhD at the Graz University of Technology.
Welcome to Bridge the Gap, the physics-oriented podcast,
in which we give insights into various research topics and the life of scientists.
And by the way, if you want to contact us, you can drop a line to our email address, bridgethegap@tugraz.at. Hey Daniel.
Hey Tommaso.
Today we're going to talk about ultrafast spectroscopy, a very hot topic in physics. You ready?
For the interview, yes. For your jokes, barely.
You know what? While preparing the intro, I rehearsed a couple of jokes I wanted to tell you during this episode, of course, with some friends of mine. Only to realize they weren't so funny after all.
Yes, and in other news, the sky is blue and the grass is green. Are we done stating obvious facts?
Hey, it's not that easy to come up with jokes about something happening on a timescale as fast as 10 to the minus 12 seconds or so.
Not even 10 to the plus 12 seconds would suffice.
Also, I tried my best to slow them down, but all my jokes were so fast they were over before anyone could react.
Well, fair enough. I must admit, they were your best ones yet.
Anyways, we asked some students and colleagues of ours what they knew about ultrafast spectroscopy.
And that is what they had to say.
Ultrafast spectroscopy is a kind of spectroscopy that is done on very short timescales, down to attoseconds, I believe. And doing that, it should be possible to actually see the electron dynamics.
I don't know which kind of unit you want to have. Is it like light years or h, or is it like turtle speed? I don't know, but I guess it's kind of fast.
I mean, it's called ultrafast, so I would say it's like Ferrari kind of fast and not turtle kind of fast. I guess maybe if you have a microscope that is big enough to show you the electrons, because they're really small, I think.
I do not know what is ultrafast spectroscopy, but I will just say a number or an order of magnitude of nanoseconds. And if we can see electrons in evolution in real time, I am really not sure, but I would say maybe by now we're able to do so in near real time.
So it is our pleasure today to welcome to the show Peter Puschnig from the University of Graz. Peter, would you like to introduce yourself? Tell us about your background, field of expertise. Stage is yours.
Yeah, thanks, first of all, for the invitation. So, yes, I'm a professor in theoretical physics at the Uni Graz. And I'm working in the field of electronic structure theory. Yes, I'm also involved in teaching. Some of you might have encountered some of my lectures in the beginning. I'm teaching a differential and integral calculus in the first semester, but then later in the masters, I also have a specialized course on electronic structure theory. And I guess that towards the end of this interview, you kind of get to know what I'm working at.
Then let's start with something very basic. What even is an electron, and is there any intuitive way to think about it?
Well, actually, that's not a super easy question for a start. I mean, the way we think of electrons, it's one of the fundamental building blocks of nature. So and we assign to it certain properties, like it has a mass, it's about 2,000 times lighter than a proton. It has an electric charge, a negative charge opposite to the one of a proton. But it also has a strange property called spin. So one can think of it like having an angular momentum. Yeah? And connected with the angular momentum, there's also a magnetic moment. So it behaves a little bit like a needle of a compass. So if placed in a magnetic field, this magnetic moment can also align according to the magnetic field. When it was discovered, the electron, people thought it's like just a little tiny ball, but nowadays we know it's more like it has both properties. It's properties of a wave and of a particle.
Does the electron behave differently if you have the free electron or if you have electrons in a compound? So what's the difference between free and bound electrons?
Well, a free electron, so if it's free in vacuum, then it can basically have any energy. You can continuously change its energy and momentum, and there's a defined relation between energy and momentum in free space. The difference, if it's bound, for instance, by the electric pull of an atomic nucleus, it's like bound to the atomic nucleus. As any quantum mechanical system, if it's like in a well, if it's captured, then the energy can no longer be continuous, but an electron can only have discrete energy levels. And actually, that is one of the success stories of quantum mechanics, that it could explain the discrete spectrum that we record from an atom, for instance. Yeah.
So, since we talked about bound states now, this is also a good way to get to matter in general, I guess. And intuitively, if you look at an atom, the nucleus is much, much smaller than the whole atom, right? So there's a lot of empty space actually, or like all matter is mostly empty space. So how can it even be that it is solid, or that there is something connecting?
Yeah, that's actually a very interesting question. I mean, you're right. I mean, you can just get this picture about the relation of sizes of the atomic nucleus to an atom. For instance, in a hydrogen atom, diameter of about 0.1 nanometer or 1 angstrom, whereas the nucleus is much smaller. So if the nucleus were the size of an apple, then the electron would be like kilometers away from this apple. And first of all, the electron is not a point-like object, it's more a wave, so it extends. But that's not the main thing why we cannot, for instance, if we push with our fist on a table, cannot penetrate the table. It's really a quantum mechanical effect rooted in the fact that, well, I should explain first that electrons are so-called fermions. So fermions are particles which have the property that they have a half-integer spin. And it turns out that if you have many of such fermions, the many particle wave function, in our case the many electron wave function, needs to be antisymmetric if you interchange two electrons. So in simple terms, this Pauli principle means for an atom that any two electrons cannot occupy the same quantum state, which means that this kind of leads to a so-called Pauli repulsions. Essentially, when I hit with my hand the table, the electron clouds in the atoms of my hand, or molecules of my hand, try to penetrate the electron clouds of the table, but because of Pauli principle, this is not possible. And then you feel a pressure, and that basically is the reason for the stiffness of matter, I would say.
So even without the repulsion due to the equal charge, there is a repulsion within
Yeah, man, of course you're right. I mean, there's this effect that the electrons, of course, they are negatively charged, and because of Coulombic repulsion, there's a repulsion. But I think the stronger reason is really this quantum principle of Pauli repulsion.
That is very interesting. So right now you mentioned the fact that electrons are more or less diffused in space, so they are waves. And also you mentioned wave function. So what is a wave function? Why do we need it? And what about its properties, like symmetrized, anti-symmetrized?
Well, maybe I'll start a little bit historically. So I mean, when the electron was discovered in the early 20th century, I guess, they thought it's a tiny particle. And then people like Niels Bohr tried to understand atoms, like a simple hydrogen atom, in pretty much the same way as we describe planets orbiting the sun. So the Bohr model still kept up the idea that electrons are orbiting the atomic nucleus. But then it was soon realized that this leads to contradictions. For instance, because of conservation of angular momentum, that would mean that the atoms are disks, not ball-like as we experience them, and also more severe because of the electric charge orbiting around a nucleus. That would be an accelerated motion, and the electron would lose energy and would soon fall into the nucleus. And then it was discovered that with this Bohr idea, with additional assumptions, one could describe the hydrogen atom to a sufficient degree, sufficiently well. But more complicated atoms, larger or molecules, it was not possible. And actually, this very year we celebrate the 100th birthday of the invention of quantum mechanics as we know it today. So people like Heisenberg and Schrödinger and later Dirac, they developed what Schrödinger called wave mechanics and Heisenberg called it matrix mechanics. And the central quantity in this wave mechanics is the so-called wave function. Finally coming to your question. So instead of describing electrons as particles described by the position and momentum. A wave function is an object, a mathematical object, which describes the probability to find electron in a certain part of space. And the equation which governs the dynamics of this wave function is the Schrödinger equation.
So then is the wave function the same as the orbital, sort of, which also describes the probability? Is it the same thing?
Yeah, it's you can think of it in simple terms as the same thing. If you a wave function in general in technical languages, that wave function typically means many electron wave functions. If you talk about orbitals, then it describes the wave function of one single electron in a given state. So that's maybe the distinction. Wave function is more general, describes also wave functions of many particles, whereas orbitals describe the wave function of just one electron.
So, in a sense, you already hinted at the answer in here. So there is a difference between wave function and orbitals, because the orbitals, as we know them, have been derived from the solution of the Schrödinger equation for hydrogen. So then, which is the range of validity, if you want, when you want to use, wave orbitals for many electron systems?
Yeah, I mean, this is something that you learn in fourth semester of your physics bachelor, that the Schrödinger equation is easy to write down for complicated situations, but it's really difficult to solve, at least analytically, for many problems. There's only a few problems where you can solve Schrödinger equation exactly. And what you learn in the fourth semester is how to solve it for the hydrogen atom. And then it turns out that you find these beautiful electron orbitals of the hydrogen atom. Like some of them are spherical, some of them are like dumbbell shape, and so on. And your question is, why can we still think of electrons in atomic orbitals for more complicated atoms? Even the helium atom, which only is slightly more complicated, having 2 electrons and atomic nucleus with 2 protons and 2 neutrons, we cannot solve the Schrödinger equation any longer exactly. We can solve it numerically, but we can still make use, we kind of use the atomic orbitals of the hydrogen atom as building blocks for describing in this case, the 2 electron wave function. And by making use of the Pauli principle, we know how to arrange these building blocks in so-called Slater determinant that fulfills this antisymmetry property. And that's why we can still describe many properties of also more complicated atoms and molecules with the help of these simple orbitals. Of course, the interactions between the electrons then modify the atomic orbitals of hydrogen slightly, but it's still a useful concept also for more complicated objects.
So also for molecular orbitals, so can you infer from these hydrogen orbitals of 2 atoms what molecular orbital they would form or how they would form one?
Yeah, so for carbon there is the s orbital, which is spherically symmetric, and the p orbital, which is like dumbbell shaped. And they can also what is called hybridize and form new orbitals, which determine then the way that carbon atoms interact with each other. For instance, you know that there's graphite and diamond are both made of the same sort of atoms, carbon atoms, but they have completely different properties. Diamond is super hard, transparent, doesn't conduct electricity, has no electric conductivity, whereas graphite is black, is quite soft, actually used as a lubricant, and it's conducting electrons. And the reason is that basically the electrons are in different orbitals in diamond. In diamond, they're in a so-called sp3 orbital, which means that each carbon atom can form bonds to 4 neighboring carbon atoms, and then it gives this rigid structure of diamond, whereas in graphite, it's in a different orbital, sp2, and then it only has 3 carbon neighbors, and there is 1 electron left, which can do the conduction, and that makes all the difference between carbon and graphite.
That's really fascinating how 1 electron can change things.
Yeah, that's actually part of my research to predict properties of materials by starting from the basic principles, which in case of electrons is the many electron Schrödinger equation.
Maybe you could explain to us what techniques there are to investigate the electronic structure of materials.
Well, I mean, if you talk about, if you want to learn about the structure or the electronic structure in particular of material, in simple terms, what you do is you shoot some sort of particles on your piece of material that you want to investigate, and then you detect the particles that are scattered or emitted from this material. And depending on the type of particle that you shoot on and the type of particle that you detect, you can learn different properties from your material. Maybe to give you an example, you can use X-rays, for instance. You can use X-ray photons or X-ray radiation to investigate the atomic structure of a material. This is actually, if you look at X-ray photons that elastically interact with your materials, that means that they do not exchange energy with your material. So or in other words, the incoming and outcoming wavelengths of the photons is the same. Then the technique is, by the way, it's called X-ray diffraction. Then you learn something about the structure, the atomic structure of your material. Another way of learning something about the electronic structure is to, again, use X-ray or UV photons, and you shine them onto your material. And then some of these photons, they will interact with the electrons. So they will actually get absorbed. So they exchange the energy with the electron. Then the electron, if it's close to the surface, can leave the material. And then if you happen to have your material in vacuum, then the electron can fly to a detector and where its energy and momentum can be detected. So that's called the photoelectric effect, which is the basis of a spectroscopy called photoelectron spectroscopy.
And from this electron, you can reverse engineer the electronic structure?
Yes, kind of, because actually this is what Einstein told us in one of his famous papers from 1905, so where he explained this photoelectric effect. Basically, the core of this paper is just the energy conservation, which tells us that the photon has a certain energy, and the electron that we detect basically needs to overcome some binding energy, and then once it's free, the rest of this energy of the photon is the kinetic energy. And if we measure the kinetic energy, you can learn something about the energy that the electron had when it was bound in your solid.
That's really, really fascinating. Another technique that I read about when I started digging into your research is this photoemission orbital tomography. So can you tell us what it is exactly? How does it work?
It's actually very much related to photoelectron spectroscopy. In fact, it is photoelectron spectroscopy. But in addition to detecting the kinetic energy of those emitted electrons, one also detects the angular distribution. And it turns out that this angular distribution of the emitted electron is not just arbitrary. So actually we can apply the principles of quantum mechanics to learn how to describe or to calculate the probability of electrons to be emitted in a certain direction. And it turns out that what we measure is actually an image of the orbital, although not in real space, but it's rather an image in so-called momentum space. So we get the momentum distribution. So what we measure is the momentum distribution of the electron that it had in that particular orbital from which it had been emitted. And with the help of a little bit of mathematics, we can transform this momentum distribution using a so-called Fourier transform to a real space distribution. We kind of measure we measure an orbital, or at least an orbital density, because I didn't go into that before, but quantum mechanical wave function is a complex quantity. So it has a real part and an imaginary part, or in general a phase. That phase cannot be measured. We only measure the absolute value of that orbital. But still, it's really a useful and really fascinating property that we can measure that way.
And this technique can be used to track the motion of orbitals then?
Well, actually not, because not directly, I would say, because, one of the fundamental principles of quantum mechanics is also that the act of observing something changes the system. So it's quite clear in this photoelectron spectroscopy. Once we kick out the electron, it's no longer there in the orbital, so we cannot follow its motion any longer. So, yeah.
So what do you do?
Researchers are quite creative. So what we do is actually we capture the motion of the electrons in using what is called a spectroscopic technique. You may know what it is. So it's basically, if you have a motion of some object under a dark background, then you can capture this motion by using some light flashes that illuminates the object at some very short times. And if you have these light flashes coming at regular intervals, then you can get an image of the motion of this object. And that's at the heart of so-called pump-probe spectroscopy that we use to capture the dynamics of electrons.
So since you mentioned the pump-probe experiment, could you explain what it is exactly?
So in a pump-probe experiment, one uses two laser pulses, one the so-called pump pulse, and the other one the probe pulse. The pump pulse excites the electron from one particular state, typically the ground state, so the lowest possible energetic state of the electron, to a higher lying state. And then the second pulse, the probe pulse, which follows the pump pulse with a defined time delay, may kick out this excited electron. And then we detect the electron, as I explained before, using its momentum and energy. And then, of course, I have to repeat this pump-probe sequence millions of times, because every time I just basically get one or just a few electrons. So I have to repeat this sequence of pump and probe pulses many times. So typically, in these experiments, there's, say, 100,000 pump and probe pulse sequences per second. And then this experiment runs maybe for minutes or even hours until we get enough emitted electrons to get an image of the orbital in a particular state. And this is now just for a particular time delay between pump and probe. But then we can redo the experiment, change this time delay between pump and probe, and get the state of the electron at a later time after the pump pulse. And that's how we get basically still images of the dynamics of the electron, and that we can, in the end, put together and have a kind of a movie of the electron in this excited state.
So we're doing electron photography.
Kind of, yes. But we photograph them not in real space, but in momentum space, and the time scale is also super short.
What is it that you want to unravel with this technique, this orbital cinema project?
The kind of questions that we want to answer is, in one of the experiments, we look at a certain type of molecules called organic semiconducting molecules. You may have a mobile phone with a so-called AMOLED display, which is OLED means organic light-emitting diode. So there are organic molecules, so basically built out of these carbon atoms that we mentioned previously, that have interesting properties. For instance, one can make light-emitting diodes out of them, or the other way around, one can also use the photovoltaic effect. So one can make a great electric current by shining light on these kind of molecules. And one of the processes that we want to understand is, if you shine light on such a molecule, it creates an excited state called an exciton, where the electron is still bound to the molecule. But if you want, in an organic solar cell, if you want to create an electric current, the electron needs to be separated from the molecule. And this process happens at the femtosecond time regime. And we want to basically film this process, how an electron is detached from one molecule and hops to another type of molecule, because it's not just because it's cool to film this, but once we understand this process, we hope that we can also suggest how to improve it, so that we can, maybe in one day we can make more efficient organic solar cells.
I'm looking very forward to seeing this video. When do you think it will be available?
The first experiments are already done, and there's one paper coming out soon, hopefully, where we not exactly do the experiment that I just described. It's because for that we need a more complicated sample with 2 type of molecules. In the first experiment, we demonstrated that this idea works with one sort of molecule where we already see some dynamics, and we learned something about the size of this so-called exciton and how it actually changes within 100 femtoseconds. We see that there, because of electron-phonon interaction, it shrinks a little bit during the first 100 femtoseconds, something that no one has observed before. Yeah.
That's really interesting. So really looking forward to this movie.
But what are the main challenges, you would say?
One of the challenges is that some of the lasers you can buy commercially. You need to compress the laser pulses such that you get, for instance, your pump pulse is in the optical regime. And that's also some technique, but that's kind of standard, I would say, to compress these pulses such they are only, say, 20 femtoseconds long or something. More challenging is probably the probe pulse, because I didn't explain this, but in order to get high enough electron momenta in the end, this probe energy needs to be in the extreme ultraviolet. So it needs to be in the order of 20, 25, 30 electron volts, which is no longer in the near UV, and you cannot just use normal lasers. You need a technique called high harmonics generation. Actually, the Nobel Prize of last year was one share of it was awarded for the techniques to generate such pulses. So this is one challenge, to get these pump probe pulses. And then you, as I explained before, you need to make sure that the time delay between your pump and the probe, say 30 femtoseconds, is stable for hours, which means no thermal fluctuations in your room, if possible. Because as soon as you get thermal drifts, they get things expanding, and then all the path lengths are changing, and that would change this time delay. So you need to have super modern labs to keep the temperature as stable as possible. And then another aspect is how do you actually detect these electrons? In theory, it sounds quite simple, just detect the electron as a function of energy and momentum, but in practice, this is also not super easy. You need a so-called momentum microscope. Everything needs to be done in ultra-high vacuum. And yeah, just to give you an idea, I mean, one of the experiments that we are planning to do in our project, which runs for 6 years, here we want to really go to the attosecond time regime. And there, my colleagues in Regensburg, they ordered a new laser system, which costs about 1 million euro. And they build it up now since 1 year, basically. And it's still under construction, so to speak. So it takes really something to get these things working.
I'll never complain about the theoretician work anymore.
Yeah.
Okay, I think on this note we can conclude the episode. So Peter, it's been a pleasure to have you here, and thanks for enlightening us.
Yeah, thanks for having me. It was really a nice conversation, yeah.
Thanks for listening.
And hear you next time.
And by the way,
if you want to contact us, just send a mail to bridgethegap@tugraz.at.